Okay, we are going to see error in the GPS measurement. This is I propose to use a classification. Sorry, the color is not good. We have different color, but I don't know why. I don't know why. After I'm going to check. So we can classify the error in instrumental error, modeling errors, measurement error, processing error. And these are reported some examples of errors that we are going to see in detail. So the instrumental errors mean that the theoretical errors that we have seen using this empirical rule, 1–2% of the wavelength of the signal. So in the code measurement, our signal is a modulated signal carry. So is related to the wavelength of the pseudo-random noise code that we are going to use, the CA code or the P code. And for the phase measurements, this means phase, sorry, we have already seen that we have very high precision from a theoretical point of view. So we are going to see that we have to take into account also for other errors. For instance, the modeling error. The modeling error could be error due to the clock biases, orbit biases. So we have seen that we have this problem in the synchronization of the clocks, the satellite and receiver clock, but also the synchronization between satellite clock. We can have a bias of the orbit because we are going to see that within that this orbit are known, the satellite orbit are known with high precision. We can have a problem due to the propagation of the signals through the atmosphere. And these problems are in common for code and phase measurement. For the phase measurement, we also have the problem of the initial ambiguity of the phase of the carry, and also another problem called phase center variation. So some errors are common to both the type of measurement, others are specific for the phase measurements. We are going to see in detail. Okay, modeling error, clock bias. We have discussed before, is an important error. In fact, the system has been built, designed to see at least 4 satellites all over the world. In any point of the Earth, I need to see at least 4 satellites for real-time positioning, just to solve the problem of the synchronization between satellite and receiver. We have also to solve the problem of the synchronization between the satellite, clock satellites, but this has been seen including in the orbit error, orbit biases, because the correction of the satellite clocks are given with a high precision orbit, and now we are going to see. So we have to take into account for the motion of the satellite, and the satellite are moving, of course, in the Earth's gravity field, so can be subject to the variation in the Earth's gravity field, and also by the tight attraction due to the motion to the attraction of the moon and the sun. There is the problem due to the solar radiation pressure. We have introduced this aspect when we have talked about the orbit of the satellite in the first lesson. And the non-gravimetrical effect on our gravimeter, for instance. The hertz have not. We have also motion of the hertz, so we have two bodies that are with a relative motion, the satellite and the hertz. The motion at the hertz are due, of course, to the lunisolar solid-hertz tight, irregular rotation of the hertz. You know that the rotation of the hertz have some particular rotation aspect about global. Okay, no, sorry. Okay, later. And we also have a problem due to the ocean, the atmosphere, and so on, the loading of this quantity that are changed over time in the space. So we need to know the satellite position, because we have seen in the equation in this quantity d, the distance is the range between satellite and receiver. We have the coordinate of the satellite, x receiver minus x satellite square, plus is a very simple equation. Okay, so in the equation of the range, we have the coordinate of the satellite, and these coordinates are supposed known. And we know that in the D message of the satellite, we receive this position. We receive the ephemerity, the parameter that we need to compute the satellite position over time. We don't obtain exactly the coordinate of the satellite, but the parameters that give us that can be used to compute the orbit of the satellite. We have seen that we can express the areas as a satellite position can be expressed in terms of Kepler element, 6 element, and in this equation we have to introduce a perturbing force. So in this representation I put these 6 elements. Are not so important now, but just to show you. Okay. Okay. The parameters that are transmitted with the D message are called broadcast ephemerides, and are in the D message. And these positions are predicted positioning, are not observed. It means that now I can, the master station can predict where the satellite will be in the next month, for instance, in the future. It's predicted using the knowledge of the gravity field and the perturbation effect and so on. But it's not measured, it's predicted. So it means that given a day X, we have a prediction that okay, it's complicated. Available. It means that I don't know. I write in this string notation. Okay, it is important that we predict the position of the satellite, and this prediction will be available for day after. Sorry, plus, not n. Minus plus. So we compute now the position of the satellite for the next month, for instance. Okay, and we have this prediction recorded in files of 24 hours. Okay, so the position for each day in the future. these are predicted, and for many applications are not sufficient. The quality of this prediction. For very high precise positioning, we need to know exactly where is, exactly more or less, with a centimetric precision of 2.5 centimetric precision, where the satellite will be, was during our measure. So this is, there is a center called International GNSS Service. In the past was called International GPS Service. It was a service born in 1992 that compute and give in a free way some products related to the orbit and the satellite clock. So we can have available on web the so-called IGS ultra-rapid product in terms of orbit and satellite clock correction, IGS rapid product or IGS final orbit. We are going to see in detail. So IGS is a service. It's based on geodetic community, and they use observation of the GPS station distributed all over the world, more or less. So of course, there are some part of the world where there are more stations, and other part less. It depends, of course, by the condition. Geographical and political condition, but they produce, for instance, ultra-rapid product. Ultra-rapid product, if you consider a day X, the orbit for this day will be available the same day plus with a delay of 3 hours. And this every 6 hours they update this estimate. So we have a ultra-rapid product orbit at 3 o'clock, 9 o'clock, 15 o'clock, and 21 o'clock. And these observations are collected in file where are collected the position for 48 hours. The first part of the file, the first 24 hours, the observation related to the 24 hours, has been computed uses the most recent GPS observation. The last part of the file are in part prediction of the position. But with respect to the broadcast ephemeris can be computed now for 2 months. So it's a long-term prediction. In this case, we use the observation of the satellites, the most recent observation of the position of the satellite. And we compute the position of the satellite in the future using the most recent observation. So the prediction is better than in the broadcast file, because it's more related to the real situation. You can understand it's difficult to say now, it's a different examples. But for instance, for weather forecasting, I can say, okay, in a month, I suppose it will be high pressure, so the weather will be, I don't know. But I can also say, okay, tomorrow I have collected wind observation, pressure observation, temperature observation, and so on. I can suppose that the weather tomorrow will be sunny. I suppose, I checked. So it's a more realistic prediction. The same with the ultra-rapid product. They use the most recent observation, but they are going to predict. And every 6 hours they change this prediction. So this 48-hour file doesn't start, for instance, at midnight of a day and finish at the midnight of 2 days later. It's a shift in time. It started, for instance, at 3 o'clock, 9 o'clock, and so on. The 48 time are not correlated to the day, but are just this time, interval time. So this type of product are really important because are important for real-time application. For instance, GPS, we're going to see at the end a lot of application of GPS. One of the application is in the study of tsunami. When you have an earthquake and you want to give information about tsunami, you need real-time observation because you have to give an alert, for instance, in some part of the earth. So you need a good product to be realistic in your prediction. Okay, so for instance, this is one application of the IGS ultra rapid product. Of course, for this type of application, we don't need a millimetric precision in the positioning, but a reliable positioning with a good position in real time or near real time. This is near real time. We have another type of product, rapid product. Given a day X, we take the observation of this day and we obtain this orbit the day after with a delay of 17 hours. So these positions are based on the observation of the day before, on all the observation. In this type of product, we don't have any prediction. It's based on the measure. Okay. And for this is not so used for real-time application because you have to wait the day, all the day to have the solution. But if an earthquake occurs in day X, the day after 17, you can use this orbit for your GPS observation to give a cosmic displacement in a very near real time. It's not real time, but very fast.
Okay, so it's not prediction.
It's not prediction, so you have to wait 1 day, more or less. The final product, this is SP3, is a dot point SP3 is the name of the file of the final product. You have observation day X and the results, the orbit, are available later, every Thursday, but so you have to wait at least 10 days. Why? It means that if you have observation this week, you have to wait all the other next week plus today. You understand? So we observe now that on Monday we have to wait for next week.
Wednesday?
No. Today is Monday. I collected GPS data today. To have the final orbit for the observation of today, I have to wait all this week, the next weeks, and we obtain the observation Thursday of the other week. So more or less we have to wait for 10 to
Next Wednesday.
yes, Thursday, not Wednesday.
Today,
Monday.
1 week, and after 1 week,
We have to finish because this product are given in daily files, but in a block of all the week. We have to wait for all this week.
8 days.
Yes, 8 days. Yes, but the time is more than 8. So we had.
It's just because they are distributed this way. So.
Yes, are distributed in a week basis. So we have to wait for the end of this week. After they process all the day of this week, and after 8-9 days, they give us the solution. So it means that now it's Monday, I have to wait at least a week to have the final product. But are the more precise position of the satellite. And why we have to wait for so long time? Because it's a combined solution. We have GPS station all around the world. For this station, we're supposed to know the position of this station because are observing for a very long time. At the end, they don't compute the receiver coordinate, but they compute the satellite coordinates. They invert the problem. And there are different center of analysis, GPS analysis data, and any center use different approach and so on, different subnetwork, I suppose. At the end, they combine together all these solutions to get the best solution, the final solution. So this is why we have to wait for a long time. In the rapid product, I don't remember well, but I suppose that is not a combined solution, just for the IGS, just from one center of analysis. Okay, so they have to combine all this solution and give us the solution. For geophysical application, for when you don't have problem with the time, you don't have to do tsunami hazard or give rapid information about seismic displacement and so on. You use IGS final products in your process of the data to give the position of the receiver. This is a file. I realized that I don't show you some slide in the previous lesson that I put today. I put, okay, after. It's not so important, it was about this. Probably I put, no, it was at the end of this lesson, sorry. Okay, don't worry, we can see later. Okay, this SP3 example is a ASCII file, so you can read the number inside. And it's important that we have information about your reference frame. This was an old file in IGS 05, and now the reference frame is IGS 14. Do you remember what is a reference frame? Is the realization, the materialization of our reference system. Is a set of coordinate and velocity, plus error and so on, of station around the world. Okay, it's important to say, because when we compute this equation, it's important to know in which reference frame. So we know that from this file, that the coordinate of the satellite will be in, for instance, this reference frame. And okay, there is the list of GPS satellite, and this is the epoch 2011, 24th of January, time 0, hour 0, minute 0, and second 0. We have this satellite position for this satellite, satellite 1, 2, 3, and so on. These are more or less the most important. We have also information about the clock to correct the satellite clock for each satellite, you see. So in final orbit, we take into account also for the clock correction of each satellite. Just for real-time application, we don't take into account of this difference, and we say, okay, all the satellites are synchronized. Okay, but this file is written written by the is read by the computational software. Okay, this is for the orbit. That is one important thing that we have seen. So we can use IGS product to solve the errors that we can have in the position of the satellite. I say that the final orbit has a precision, nominal precision of 2.5 centimeter. We're going to see that we want to reduce also this error.
What does that mean? Sorry.
The precision in the position of the satellite is equal to 2.5 centimeter. Okay. But for the physical application is too high, this error. But we are going to see how we can reduce also these values. Not with modeling, but with another approach in the data processing that we are going to see after. Modeling error, we have we have also to take into account on the motion of the Earth. So the Earth is have deformation due to the mass distribution due to the ocean tide. So we have to take into account also for this, and this this is the reason the Earth deforms itself under the load of the masses of the water on the ocean bottom, because it's not a rigid body. So we have to take into account for the water distribution and for the loading of the water on the bottom of the ocean, more or less. And for this reason we have vertical and horizontal displacement that can be or change in the gravity field or tilt or strain. So we have a periodic distribution of the ocean masses, and so we need to take into account for ocean loading correction. And there is a website that they use different model to, and given a station they predict, they say which is the effect of the ocean loading, station by station. You give the coordinates and they compute this deformation. So this they use in this type of application you use an harmonic development, and is enough to use 11 coefficient, harmonic coefficient. In this picture is represented harmonica and 2 that have a period of 12 hours and 25 minutes. So you can see the amplitude of the tide, where is more or less for this term. And so if you go to, when you have a new station that you have to you put your GPS in a new benchmark, and now you collect data and you want to process this data to have the position of this benchmark and to start a time series, a daily solution for this station. The software, that scientific software, we are going to see this, the software that give us the highest precision in the positioning, ask you for a file that take into account for the ocean loading. And so you have to go to this website and choose a model. There is different models. This is one of the most used, and compile and fill all this field, and you obtain a file that you can introduce in your software. These files are in BLQ format. It's a standard, but just to say, okay, I have to take into account for this probably the software stop if it doesn't find your station in this file that have all the information about the ocean loading. The ocean loading means that are related to the tide, a very predictable signal. So if you give an approximate position of your station, and you can give very simple, because GPS was made to give you a position in real time. So you can have you can have an approximate position for your station. It give you information about the deformation due to this type of the tide and the ocean loading. Is a once for every time. It's not changing over time. This type of approximation of correction. Okay. You can see in the website, in some part of the hertz are more precise, in other part less. It depends. For instance, if you are in a sea basin very shallow, like Mediterranean, like Adriatic sea, the station along the coast cannot have a very good prediction using this model. It depends on the model. But if you have a station in a highland in the ocean, the prediction is very high. It depends also by the amplitude of this effect. Okay. So, we have seen problems related to clock and orbit biases. Now we are going to start. Oh, sorry, it's time for the break.